My name is Jim, and today we're going to be discussing decibels part 2, specifically current and voltage. And from part 1, what we know is we can measure power using 10 times the log of power out over power in, or in the case of dBm, 10 times the log of power out divided by 1 milliwatt. Now, when using voltage and current, things are a little bit different. And if we just back up a little bit into Ohm's law, what we see is that P is equal to V squared over R, which is equal to I squared R, and is also equal to the voltage times the current. Now, what we're interested in here is this square. And if you say, well, I don't see a square in VI, that's correct. However, if I were to substitute V over R for I, this is what I would get and end up with V squared over R. So when you're dealing with voltage or current, there's going to be a square involved in the calculation. Now, what we know is that if we exponentiate in the linear domain, we end up multiplying in the log domain. So raising a number to a power, instead of using 10 raised to the 2 or whatever, some voltage raised to the second power, all we have to do is multiply in the log domain. And we would do that simply by, if we take, for example, an amplifier with a voltage out and a voltage input, the decibels in voltage now, the ratio, because decibels still are a dimensionless unit, would be equal to 2 times 10 log of V out over Vn, which, of course, just combining these together gives us 20 log of V out over Vn. Now, it's important, critically important, that you use 20 when you're working with voltage and current, and 10 when you're working with power. If you don't, it's most likely, unless you're dealing with unity gain, that your answer is going to be incorrect. So, for an example, suppose we have an amp with a gain of +9, and we wanted to find out what the gain of that would be, and suppose we measure V out to be 18 volts, and as long as the units are the same in peak or RMS for V out and Vn, and we're going to get the same correct answer. And substituting in here, I write down the general form like I always do. It's always a good idea to do that, I think. And decibels equals 20 log of 18 over 2 volts, and it comes out to a gain of plus 19.08 dB. So if we were to use one of our multimeters in decibel mode, not normalized, that's the value we would read. Now, suppose we have this circuit. Pretty simple guy, 2 resistors, and what we know is we have a 1 to 10 voltage divider here, 9K and 1K, and then working out V out relative to Vn, as we see that it equals Vn times 0.1 volts, and then getting it into the correct form would be dividing both sides by Vn, which gives us a gain of 0.1 volts. So figuring that out in decibels, we have 20 times the log of V out over Vn, standard stuff, which would be 20 times the log of 0.1, which would give us negative 20 dB gain. So the output is going to be 20 dB down from the input, or we could say the loss, and I put a plus here deliberately, is 20 dBm, dB rather. And the word loss means that the output is lower than the input. So loss has a meaning to it, much like ripple rejection ratio. Now, for another example, suppose we take this guy, and this is a buffer. It's an operational amplifier set up with 100% negative feedback. And V out very, 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 very closely is the same as Vn. So under that circumstance, if we were to find the gain of this, and what we can see is that that's going to be unity in the linear domain, it would be 20 times the log of V out over Vn, or 20 times the log of 1, which would give us 0 dB. So if we go to chart this like we did before, 0 dB is unity gain, Anything greater than 0 means that the output is going to be larger than the input, and anything less than 0 means that the output is going to be, anything greater than 0 means that the output is going to be greater than the input, in case I said that wrong, and anything less than 0 means that the output is going to be less than the input, as we can see with this simple voltage divider here. So if we graph the log of x, it looks something like this. The log lives in quadrants 1 and 4, and if you step outside of that, your calculator should complain. In graphing this, we end up with an asymptote as we go toward the negative y-axis, and in quadrant 1 we grow without bound. So, and this is this is 1 here. So what we could say about that is that x raised to the 0 power is equal to 1. Yeah, x raised to 0 power is equal to 1. Now, this grows without bound, which means that if we, I suppose, took the most powerful thing in the universe, which is a quasi-stellar something, a quasar, brightest object in the sky, we could measure that, I suppose, in dBm. And since this grows without bound, it would be a very, 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 very large number. So that's the general shape of a log. And note that it never enters quadrant 2, and it never enters quadrant 3. Okay, suppose we have this guy, a averting amplifier, very simple op-amp, and we have 9K in the feedback path and 1K in the input path, and this here is a ground. This is an inverting amplifier, and the gain equation for this is, I need to put an approximate there, approximately equal to negative RF over RI. Now the approximately equals, I really could put an equals, because with a contemporary operational amplifier, it is so closely determined by RF over the input resistance RI is that, you know, the equation is just about perfect. Totally swamped by the tolerance of the resistors. So if we work that out, is what we see is we get a gain of -9. Now what that basically means is that our input signal would be of this polarity, and our output signal would be 180 degrees. This polarity, and let me draw a line through that. So all the negative means is that the output phase is reversed by 180 degrees. Now if we go to find the gain of this in dB, the negative isn't going to work very well, because we would be on this side of the y-axis. So really what we need to do is put an absolute value in here, or to make it simple, always have a positive number. Decibels don't care about phase. If we look at the phasor for this amplifier, we'll see that on the real axis we have 1 volt in, and on the negative real axis we'll have 9 volts out. So it's an inverting amplifier, but it still has gain, and as long as we take the absolute value of that, we can correctly state that the gain in decibels is equal to 19.08 dB. So logs do not understand phase. It's not about that, it's about levels. Okay, it's got another example here. In this case we have an amplifier with a gain of 18 dB, and we're told that the input voltage is 100 millivolts, and the question becomes is, well, what is the output voltage? So we would set this up. 18 dB is equal to 20 times the log of the out over, and the input in this case is 0.1 volts. Now the reason I express that in voltage with a leading zero is, leading decimal point rather, is because the output is going to be in voltage, and the units of this have to cancel. So remembering that 18 is a dimensionless number, I'm going to try to isolate the variable and divide both sides by 20, which will give me 0.9, equals the log of V out over 0.1 volts. So I'm getting there. Taking the inverse log of both sides would be the inverse log of 0.9, and the inverse log of this guy gives us access to the variable without being in the argument of the log domain. And we get, for this, 10 raised to this power is 7.94 equals V out over Vn, and now it's a simple matter to solve for V out, and that equals 0.794 volts, or V out expressed correctly would be 794 millivolts. Last example here, and while we're on decibels, is dBu, and this is used extensively in audio. And I wanted to bring it up and kind of discuss it for a minute here. There's no changes excepting for the reference value. As dBm use 1 milliwatt, we're going to have a reference value for dBu of 774.5 millivolts RMS. So this is what the meters in audio consoles are measuring, is levels in dBu. Now, how do they come about in history? Well, back in the day, in the 20s, 0 dBm was measured to be 1 milliwatt, and it was across 600 ohms. Now, the reason they use 600 ohms is that's a super common telephone impedance. And when you do that, if we solve for V, we find that we would have 774.5 millivolts. So that became the reference point for 0 dBu. Now this is super important. dBm measures power, period. It doesn't matter what the voltage is, it doesn't matter what the resistance is. As a matter of fact, it's so robust, it's actually used to measure optical power in optic transmission systems. No concern for any other circuit parameter, it's about power. Likewise, dBu is all about voltage. Typical audio system runs at a 10K impedance. Doesn't matter. Doesn't matter what the power is. It's just about voltage. So, for example, if we had an audio console, and I have 10K here just to kind of make the point, and that would be the operating Z of most of the electronics in the audio console. Outputting a sine wave at 2.4 volts RMS, what VU should the panel reader read? So we would just set this up as 0 dBu, or dBu equals rather 20 times the log of our 2.4, and note that our reference now is 0.7745 volts in RMS, and our VU should be reading 9.82 dBu. So we have basically 4 different references that we're going to be using. dBm would be 1 milliwatt. The multi-sim uses 1 volt peak for a reference. Our scopes in FFT mode use 1 volt RMS for a reference, and if you're involved in audio, it's 774.5 millivolts for a reference. And if you want ratio, there is no reference, it's just V out over Vn, or I out over In. Plus, in the industry, there's a lot of special references, like for video and things like that. So what we're learning here is the general concept of decibels, and then when you get, say, into some job that's using some different reference, you just become familiar with what that is and apply it in the way we've done here, and all should be good. So that should conclude on Decibels Part 2, and thank you for watching.